So welcome to another Tech Talk. I'm Frank Hill and I work for TriStar Plastics Corporation. This is a 101 introduction to plasma science relative to polymers. So that we're on the same page, we're going to discuss adhesion theories. Just so we get our definitions down correctly, common interactions for material when things stick together is either van der Waals, dipole interaction, or hydrogen bonding. And those are all scientific terms for two materials that are stuck together. Okay. The actual adhesion theory that we exploit the most is our hydrogen bonding. Adhesives and most of our coating materials react in this way, in that we have activated the surface so that we have a good interaction with hydrogen bonding. And if you remember from your chemistry class, there are the bonding energies off to the left there, you're right. And it lets you know that the hydrogen bonding is one of the strongest forces that we have to work with, so that's why we try to exploit it as much as possible. Under that blanket of absorption theory, we have another effect which is called wetability. So when we put an adhesive or a coating on a surface, we want it to fully wet out the surface and not leave little pockets or voids that are somewhat non-aesthetically pleasing, or they actually leave a gap where we have a reduced bonding. So we want the adhesive to totally wet out across the surface, nice smooth glass. And absorption theory, we actually require that we have the enhanced wetability. And we test that with goniometry, which is a fancy word for contact angle. The illustration just at the bottom of this slide shows a surface that is kind of normal for polymers, in that it's hydrophobic, meaning that the water will beat up onto the surface like a little ball. What that lets us know is that that is not a wettable surface. Most likely the adhesive or coating is not going to stick to that surface. It's a non-bondable surface. After we do our plasma activation or organosilane deposition, we usually get a physical trait of wetting. When we dispense the same drop of water on that activated surface, the water will flow to its maximum reach based on the quantity. When we see that property, we tend to know that, as a general rule of thumb, that adhesive or coating will stick most aggressively. Chemical attachment is really where we start to hang our hat. That's where we're exploiting our newest technologies with organosilane deposition and molecular grafting. The previous slide showed wetability, and along with wetability comes chemical activity. Now this is what you could kind of refer it to as molecular Velcro, in that these compounds are actually locking together. They're actually reacting. And this bond strength is many times stronger than hydrogen bonding. So even though we can exploit hydrogen bonding, we can even further that point and advance technology by reacting surfaces together. And if you remember from your chemistry class, which I know you all do, bonding energies are off to the side of the screen there, just so you can get a good gauge on how strong these bonds are. In organic chemistry, this is the strongest that you can get, is with covalent bonding. Mechanical adhesion is back when Jesus was a baby. They would scratch things together to get a nice rough surface. Oftentimes that will give you macroscopic roughening, so you could see that the surface is not glossy anymore. It's actually roughened. So when it comes to making surfaces bond better, roughening has always been a time-tested technique. We actually take it to another level where we actually etch the surface on the molecular level. So each molecule is being chipped and removed, so we can get exponentially a higher surface area than you would with either sandpaper or grit blasting or whatnot. And the illustration on below shows a macroscopic surface roughening, which is huge, big valleys and high hills and troughs, while the other surface is molecularly etched, and it doesn't look very rough at all. But in fact, if you were to shrink down and take a look at that, we are many times more rough in that screen than we are at the sandpaper screen. This theory of adhesion, which is diffusion theory, is really abstract. So you really got to put on your 1970s cap and go back into some sort of real abstract thoughts. When you think about diffusion bonding, it really relates to polydimethylsilicone fusing together after it's been slitted. This is all the big, long, loose chains of silicone getting wrapped up with one another, much like two teenagers with braces that kissed. They get locked up. Now it takes energy to get those apart, and you definitely have enough energy just in your hands to separate that material, but it appears in the molecular level that it has healed itself, so that slit no longer exists. But in this theory here, really where we apply our technology is that we interrupt that interaction. We take all those long, loose polydimethylsilicone polymer chains and we chop them up so that the diffusion theory doesn't work anymore. So when a polydimethylsilicone is slit, we activate it to interrupt this diffusion bonding theory, and now the slit seals, but it doesn't heal, which is important, especially for medical patients that have built-in septums due to some medicine that they have to get dosed every day. It's a painful interaction if it heals, so we make sure that doesn't happen. So just to recap the adhesion theory, we have what we want to do is exploit hydrogen bonding and covalent bonding as much as we can. And that is done with surface activation using plasma organosilanes. And when we exploit that adhesion theory, we also have side effects of surface roughening, and with all those working together in conjunction, we get extraordinary bonding strength, and we can advance materials in laminates. But plasma technology, let's go through plasma technology so that you understand. In general escape, this is one of those abstract thoughts. It's a fourth state of matter, and even though it's been well known since the 60s and used in semiconductor terms, this process is very simple. It's a 5-step process. Wherever you go in the universe, it's going to be 5 steps essentially. And the first step is our pump down step. And the pump down step, what you have to understand is that these parts are put into a vacuum chamber, and this is a batch mode process. So we take our parts, we set them into the chamber, we close the door, like your microwave oven when you're trying to pop popcorn. You put the parts in the chamber, close the door, and hit go. The machine does a process, a simple sequence. The first sequence is a pump down step. We're removing all the atmosphere in the chamber. So the parts are sitting in a vacuum. And the reason we do that is that we want to control the environment. So once all the atmosphere is gone, in the pump down step, we introduce our gas. And now this is our recipe. We put in a special type of gas in order to react with that polymeric surface. That special gas begins to flow and fill up that chamber in a constant partial pressure. As you notice that our pressure doesn't go all the way back to the top at atmosphere, it hangs out somewhere about mid-range, which means we're flowing in gas and we're evacuating gas, and that's a consistent flow cycle. As the gas is introduced, we can go ahead and start our RF time. And what does RF mean? That is true plasma mode. That's when we get a glow discharge, electricity is being introduced into the system, our gas is being introduced to the system, and bang, we're getting reaction on our polymer. This is the true magic time. This is where we're activating the surface, cleaning off organics, really modifying 360 degrees around our parts. All the nooks and crannies are getting activated. Once we deem the process complete, we go ahead and shut off the RF and gas flow. We don't need that anymore. The system comes down to its base pressure, meaning we're cleaning out any effluents that exist. And then we're able to bring the chamber back up to atmosphere so we can take the parts out. It's a 5-step process. You could just as soon put this into your house and quite easily. It's a very simple process. Push a button and it runs. Where the trick comes in is the chemistry portion, and that is the step 3. That's where you have to know what polymer we're putting in, what gas we're going to use, what effect we're trying to accomplish. Plasma chambers have general shapes and conformations based on what you're trying to do. These are 3 designs that are rather common. We have inductively coupled, which is very powerful as the magnetic field confines the plasma in the core. We have coax coupled, which is very elegant and gentle. Certain materials don't like to get ion bombardment. It damages their structure. So it's very gentle and very elegant. And then the last one is very useful in that it can be changed into so many different conformations. The parallel plate capacitively coupled, that's what we use because we can change its design on the fly. We can protect parts by putting Faraday cages. We can deposit material. We can etch material. We can clean material. We can activate, all with this design. The other 2 have a little bit more limitations on what they can do. But that's the design we choose. So if you wanted to be a good Jedi Knight and build your own, this is a simple design that you would have your gas source, the chamber with RF, a vacuum gauge so you know what pressure you're operating, and a vacuum pump. Those are the parts you need. Assemble it, and then you could generate plasma quite easily. When the magic time happens, step 3 happens, you can definitely tell something's happening inside the chamber because you do get a glow discharge. And each of these glow discharge has a characteristic color based on the gases you use. In some cases, we have the pale pink and blue, and we also have this one right here, which is a UV emission from oxygen. But those that are skilled in the art know and understand that when they see a color emission, they can pretty much tell what's going on inside the chamber. You can tell if your chamber is leaking. You can surmise what type of gas that is being used. You can understand if the plasma is being starved of processed gas based on the color change. There's a lot you can tell just by the color emission. And that color emission, when you break it down to chemistry terms, equal this mess. So those that remember chemistry class could probably read this quite well. But essentially what this means is that we take molecular oxygen and break it up. That's what that glow discharge is telling you. So you take something very simple and you destroy it, break it up into little pieces, and then and what it produces are simple combustion products. And this process is noted as being a green process because the effluents are in the parts per million, parts per billion. So the greenhouse gas emissions are next to nothing compared to solvent chemistry. Most folks would use acetones or toluene or sodium naphthalene, which are very caustic and dangerous, also adding to the VOC limits for the environment. They could opt out of those chemistries and use plasma in its place and be many times more clean and green. Now, from Tinker Toys, if everybody remembers Tinker Toys, this is Tinker Toy chemistry, where we have C's and H's all pushed together with sticks. So if you ever wondered what polyethylene looks like in Tinker Toy chemistry, it looks like that, where we have carbons and hydrogens bonded together with the sticks. What plasma will do is take off one of those hydrogen sticks and put an oxygen in its place. For chemists, that means that surface is active. And for a chemical or adhesive, that's a bonding site. That's your molecular Velcro. It's able to make an attachment there. If I take that process further, I'll begin to etch the material. And if you remember, that's one of our adhesion mechanisms. Not only are we creating bonding sites through covalent bonding and hydrogen bonding, but we can do it also with mechanical roughness. So if we just continue processing the part, we create little pits and valleys and enhancing our adhesion. So etching a polymer and activating a polymer is all a part of plasma processing. Cross-linking polymer. This is really bizarre. Put on your 1970s hat again and understand that when we cross-link a material, we actually strengthen the bond. One bond is strong. 2 bonds is stronger. 3 bonds even more strong. So in this case, how this occurs is when we have an ion, when it hits that surface of the polymer, all the molecules on that surface of the polymer get blasted and bonds are broken. And in some cases, they rearrange and go to a much more stable state. And in some cases, that's a double bond. And when that occurs, that surface is much more stable and a little tougher. So plasma processing is actually capable of doing that. Now this is where TriStar is really hanging their hat for our future, and that is coatings, functional coatings and chemical resistant coatings. So we're actually able to deposit functional coatings, which is quite important for some of our medical customers. We can take very simple and inexpensive polymers like polystyrene and coat it so that it is solvent resistant, chemical resistant completely. So they don't have to spend the money on something very expensive like PTFE. They can simply injection mold something very cheap and put on a coating for a couple cents more, and it would still be under the cost of the actual resin for something expensive. Now, atomic cleaning is kind of a side note in that oftentimes we get metal substrates. In fact, we're getting more metal now than we have in a while. And that metal has organic contamination, which interrupts rubber overmolding operations. So we receive this metal, and we're able to clean off the organic contaminants, fingerprints and oil, and then deposit a functional intermediate between the metal and the rubber overmolding. So it's not an adhesive like some of the other metal primers out there. We actually have an inorganic treatment that actually is the intermediate between metal and rubber material. Very simple applications, very likely to work for plasma, are the following: wetability, cleaning, and adhesion. If we get those applications, plasma is most likely a best bet for that. It's environmentally friendly, it's fast, and inexpensive. And all these materials fall into the category as being able to be treated. There are a few exceptions that need extra attention, but by all means they can work. PTFE, virgin PTFE, requires a gentle hand. If you're too rough with her with plasma, she totally dissociates and becomes very problematic. But with a nice gentle plasma treatment, it will work. PET, it depends on how it's been processed. If it orients itself in highly crystalline structures, that becomes quite difficult to treat. It just wards off any treatment. But depending on the processing, PET can be done. Rubber, TPU, TPR, and silicone rubber, everybody's got their own little formulation, all proprietary information. So with the company's cooperation, we're able to get there, but it takes a bit of time because everyone's got a nice new formula and no one's talking, but still likely to work. When I say it works, what does that mean? Simple adhesion terms, what we're dealing with is there's some common polymers listed here, and at the very end is after plasma treatment, after they're bonded, what type of increase of adhesion are we looking at? Some of the increases in adhesion are marginal, while some are dramatic. A marginal increase would be nylon 6,6. Nylon 6,6 in its own conformation has a tensile lap shear of around 2,000. After plasma treatment, it goes up to 2,800. Not bad, not good, it's okay. It's just a marginal increase. But something rather dramatic would be like polyethylene, where we go from no tensile adhesion to about 3,700 pounds in tensile, which is pretty much the limit of the polymer itself. Applications that are difficult but likely to work are functional treatments. This is where TriStar is heading, where it becomes a very elegant treatment for our medical companies, where we can specifically deposit carboxyl, amine, or hydroxyl on the surface of polymers like olefin, polyethylene, or polypropylene. This is important because the companies rather would like to derivatize those surfaces. They want to take these compounds, change them around for their application when it comes to DNA and PCR amplification and whatnot. We also can make the surface inert by fluorinating it. So if they don't want anything to bind to an area, we can fluorinate that so it doesn't. And to further that point, this is an example of a plasma treatment. We have 1A and 1B, 2A, 2B, and basically what this is letting you know that process 1 worked very well, while plasma process 2 didn't work well at all. And this is instrumental because not all plasma processes work the same. Plasma process 1 worked appropriately for this application, while the second process didn't. It doesn't mean the plasma doesn't work, it just means you have to choose the right chemistry. And if the right chemistry is chosen, you definitely will succeed, but it takes a good process matrix and we can get there. Very unlikely to work with plasma technique is removal of inorganic material like salt and some metals. We just don't have enough energy to do that. If you want to do something like that, you should go to the tokamak because we don't have enough energy. Okay, so to conclude this tech talk, we went over adhesion theory, and we have 4 different types. The 3 main ones that we exploit here are absorption, chemical, and mechanical adhesion. At some level, we're going to be applying that to the surface using plasma or organosilane treatments. The plasma technology that we use will functionalize, clean, and etch the material. And those are the technical terms for what we have for adhesion theory. And where TriStar is heading into the future is with our coatings. We do have USP Class 6 coating, as well as functional material coatings for metal and polymers. Thank you very much.